welcome to the lecture on vibration, isolation and force transmissibility. So, what is vibration isolation and why it is important? So, as we know that there are some machines, rotating machines or reciprocating machines, they have some unbalanced forces, and so vibrations from that machines pass to the foundations where they are connected. And so in order to stop these vibrations, we have to use the isolation. Are some sensitive instruments, they are kept on some measurement, and due to the vibration of the base, okay, so there is the vibration of the instrument, or there is some error in the reading of the instrument. Okay. So the sensitive items, they must be isolated from the foundation or where they have kept. Okay. Similarly, the vibrations coming from the machine should be isolated so that they don't reach to the foundations, otherwise they will create some vibration on the and problem to the people working on the floor. So here we have many kind of vibrations that I have discussed. So effectiveness of a vibration isolation, how do we measure? So effectiveness, we measure that if a vibration, after introducing the vibration isolation, the force transmitted to the foundation or the motion transmitted to from support to the instrument or some sensitive article, the motion transmission is reduced. So force and motion transmission is reduced, then we say that this is effective vibration isolation. So here we have some materials for the that we use for the vibration isolation. So basically they provide the stiffness and damping. Okay, they have some stiffness and damping of those materials, and we can see here some examples. So the first example you can see here, there is some machine and this is the isolator. So this is in the form of some spring. Another example is injection molding machines, and here you can see the anti-vibration pads. So there are some pads made of rubber, and they can be used as the vibration isolator. Okay. Then there are some felt or cork and some metallic springs. Okay. So these are some common materials, common components that are used as a vibration isolation. So what is transmissibility? So transmissibility, of course we are discussing the force transmissibility. So this is the ratio of force transmitted to the foundation to that impressed upon the system. Okay, so we will discuss in detail how to find the transmissibility. So we have this system. This is mass, and so this part is isolator, so it has some stiffness and damping, and this is the machine that is kept on this isolator, and this is the foundation. We want, so this system is subjected to some force F0 sine omega t, and so it is vibrating. So some forces are going to transmit to this foundation, and we want to know what are those forces. So as we have already discussed this system, because this is a single degree of freedom forced vibration system, and we have shown the vector diagram for the forces that are relevant to this system. So basically they are of course the impressed force F0, then spring force, the damper force, and inertia force. So here we can recall the vector diagram. So if we have, so this is the direction of x and this is F0 and this was the angle phi. So x lags, so in fact x was x sine omega t minus phi. So there was a phase lag. Then there was a spring force kx, then the damper force 90 degree c omega x, then there is the inertia force m omega square into x. Okay. So this is the vector diagram of the forces of this system, and this system is in equilibrium under the effect of these forces. Now we are talking transmissibility means the force that is transmitted to the foundation. Now how the force can be transmitted to the foundation? So the force can be transmitted to the foundation with the through the elements that are attached to the foundation. So what are those elements? They are this spring element and damper element. So stiffness and damping element. Through this, the force that is acting on this system is passing to the foundation. So we can make, and of course the force that are passing to the foundation, that is the spring force and the damper force, but their direction will be opposite to what we have shown here, because these forces are shown on the mass m, and the opposite forces will be transmitted to the foundations. So okay, so spring force, this is kx. So suppose this is x direction. Now the spring force kx, so this force in the opposite direction, so this is here kx, and then damper force c omega x, but in opposite direction. So this is the damper force c omega x. And if we do the vector sum of these forces, and let's give this name ftr, and here we have f0, okay, and here is this phi, and there is some angle here alpha, let's say alpha. So ftr, so the force transmitted to the foundation FTR. So FTR is the vector sum of these two forces, spring force and damping force. So it is under root kx square plus c omega x square, and so it is k square plus c omega whole square under root into x. Okay. So this is the force that will transmit to the foundation. Now what is x? So x we already have known from this vector diagram, and that x equal to f0 upon k minus m omega square whole square plus c omega whole square under root. So this is x. So we put this value of x here. So we have FTR equal to, so f0 under root k square plus c omega whole square upon k minus m omega square whole square plus c omega whole square under root. Okay, so we have replaced k with this term, x with this term. Now as we say transmissibility, of course force transmissibility, that is force transmissibility, TR equal to, we say that transmissibility is the ratio of the force transmitted to the foundation. So this is the force that is transmitted to the foundation, that is FTR upon the force that impressed upon the system. So the impressed force is F0 sin omega t, so amplitude is F0. So here we have F0. So from this equation we can find FTR by F0 is equal to k square plus c omega whole square upon under root k minus m omega square whole square plus c omega whole square. Okay. Okay, so this is the initial formula for the force transmissibility. So it says that it represents the ratio of the amplitude of the force transmitted to the foundation by the force impressed on the system. Now we take k outside, we can write root 1 plus c omega by k whole square upon 1 minus m omega square by k whole square plus c omega by k whole square under root. So I take k here outside, also here, so they will cancel out. So we have this term, and this term we can write like, so we can write this term, because c omega by k already we know that c omega by k is equal to 2 into zeta into r, and zeta is c by cc. Okay. And omega n equal to, omega n square is k by m, and r equal to omega by omega, and these things we know. So always we try to relate to finalize our formula in this, in terms of these parameters. So we have 1 plus 2 zeta r whole square under root upon 1 minus r square whole square plus 2 zeta r whole square under root. So finally we can write that transmissibility Tr equal to 1 plus 2 zeta r whole square under root upon 1 minus r square whole square plus 2 zeta r whole square under root. So this is the final formula of the transmissibility. Moreover, we can write, so this is phi and this is alpha. So what will be alpha? So here tan alpha is c omega x by kx. So c omega x by kx. So x cancel out. So c omega by k. So it means alpha is nothing but tan inverse c omega by k, and c omega by k is 2 zeta r. So we can write 2 zeta into r. Okay. So angle between transmitted and impressed force, and impressed force equal to, so it is phi minus alpha. So phi minus alpha, and phi already we know that phi is tan inverse 2 zeta r by 1 minus r square. So it is tan inverse 2 zeta r by 1 minus r square minus tan inverse 2 zeta r. Okay, so this is the angle of lag. Now we can understand, as we always do, we can draw the frequency curves for the transmissibility, because we see that transmissibility is a function of the frequency ratio, that is so the function of the excitation frequency upon the natural frequency and the damping factor zeta. So we can draw the frequency curves for transmissibility, and we can get some conclusion, some guidelines, okay, that can help us to design our system. So we can, let's see this. So here transmissibility curve I have plotted. So this transmissibility curve is for, so here we can see that this is transmissibility on the y axis, that is ftr by f0, and here is the omega by omega n, that is r. Now one thing one conclusion we can get from here. So if we do like, when the transmissibility is 1, means we want to know when the transmissibility will be 1, means the force that is impressed, that same force is transmitted to the foundation. So transmissibility is 1 in this case, or ftr equal to f0. So when we put tr equal to 1, so this equation root 1 plus 2 zeta r whole square upon root 1 minus r square whole square plus 2 zeta r whole square, this is equal to 1. Now we square these terms. So 1 plus 2 zeta r whole square equal to 1 minus r square whole square plus 2 zeta r whole square. Okay. So these terms will cancel out and we have 1 minus r square whole square equal to 1. So 1 minus r square equal to plus minus 1. So if we take 1 minus r square equal to plus 1, so we get r square equal to 1 minus 1 0, it means r equal to 0. When we take 1 minus r square equal to minus 1, we get r square equal to 2, this means r equal to root 2. So we are getting two values of r when the force, the same amount of force will be transmitted to the foundation as will be impressed on the system, that is ftr equal to f0 and that is r equal to 0 and r equal to root 2. So from this curve, if we see this curve, what we see that at r equal to 0 here transmissibility is 1 and again this is r equal to root 2, this is root 2 here when transmissibility is 1. Okay. Moreover, when r is much less than 1, okay, so for this transmissibility is 10 to 1 and when r is much less than 1, much greater than 1, the transmissibility is tending to 0. Okay. So we see that the transmissibility curve starts from 1 and near the resonance condition, that is r equal to 1, it is amplified and again it falls and and passes through 1 at r equal to root 2 and then it is tending towards 0 at the higher values of omega by omega n. So now we can get some important conclusion here. So this complete region can be identified in 3 different regions. Of course, here this first region is stiffness control region because here we have r much less than 1. It means when r is very less, so omega by omega n is less, so it means omega n is large and so omega n equal to root k by m. So we can change the stiffness of the spring. We can take some large value of stiffness and we can so we are in this region. In the region near 1, here the effect of damping is quite clear, that if we have low damping, the transmissibility is very high, and we have higher damping, the transmissibility is low. So this region is completely dominated by the effect of damping, When we come to this region, when omega by omega n is large, so omega by omega n is large, means omega n should be small. It means omega n is root k by m. So it means to have a small omega n, we must have m large. Okay. So it is large. So we see that in mass controlled region, for lower value of damping we have the better performance, means the transmissibility is less in the mass controllable region, transmissibility is less for the lower value of damping. Okay. And the overall transmissibility is decreasing. So this is the region that we want to operate our system. So we always try to keep omega by omega n large, so that we are in the mass control region. And of course, how can we change the mass of the system? So we usually, to the machines we attach some heavy concrete blocks. So we increase the mass and then we support them on some stiff high stiffness springs. So due to the very heavy mass of the concrete block, we already shift to the mass control region, and so the transmissibility of the vibrations is less to the foundation. Now we come to the phase lag. So phase lag we have already defined that the the angle of lag between the force, impressed force and the transmitted force, this plot is showing. We see that for value of damping less than 0.5, the curves are reaching to some maximum value and then falling and tending towards 90 degree, while for curves greater than damping of 0.5, the curves are they are increasing towards the 90 degree phase angle. So now we take one numerical example to apply these expressions and to understand the concept more better way. So let's start this. Okay. So we have a 1000 kg machine is mounted on 4 identical springs. So here we have 4 springs. So like here is 1, 2, 3 and 4, and similarly 4 dampers here. Okay. So there are 4 spring. Okay, so here it says a negligible damping. So we have no damper. So we have only 4 springs. So we can make these. So these are 4 springs. Okay. So, and each has the same spring constant K. So we have K, so we have M equal to 1000 kg and 4 spring is and K, they have spring constant K. The machine is subjected to a harmonic external force of F0 490. So F0 is 490 and frequency is 180. So omega is, so 2 pi into n, so 2 pi into 180 by 60 in radian per second. So we can find it is 6 pi radian per second. Now we have to determine the amplitude of motion of the machine and maximum force transmitted to foundation because of the unbalanced force when K equal to, so K is given 1.96 into 10 power 6. So first we have to find the amplitude of motion. So, for this we have this formula x upon f0 by k equal to 1 upon 1 minus r square whole square plus 2 zeta r whole square under root. So, now if zeta is 0, because we have negligible damping, we have it is 1 by 1 minus r square. So, x upon f0 by k f0 is 490. So, we have f0 by k we calculate, that is 490 by 1.96 into 10 power 6. But here we have 4 springs, so the total stiffness is 4 times k. So, it is 4 times k. So, this is into 4. So, we can compute this. So, 4 into 1.96 equal to, so it is 62.5 into 10 power minus 6. So, here in fact this we say k equal to 4 times. So, let us say this is k dash. Okay. So, this is 62.5 into 10 power minus 6 and 1 upon 1 minus r square. So, now omega n equal to root k by m, and it is 4 into 1.96 into 10 power 6 upon m, m is 1000. So, we can get so it is 88.54 radian per second. And so we can get r equal to omega by omega n, and omega is 6 into pi. So 6 pi by 88.54. So that is so it is 0.213. So we have 0.213 square. So we can find x. So we have 65.47 into 10 power minus 6 meter. So this is the x, and that is very less x. Now we have to find the force transmitted. So force transmitted we can find equal to, so we have zeta equal to 0. So we have same as 1 minus r square. Sorry, this is transmissibility. We can find the force transmitted. So first we find 1 by 1 minus r square. So 1 by 1 minus 0.213 square, and that is ftr by f0. F0 we know it is 1000. So from here we can find so here ftr equal to 1047 Newton force transmitted to the system. So here we had 4 springs in parallel. So we have to combine took the combined stiffness of this spring, and then we can apply this formula. When zeta is 0, we can simplify, and similarly we can find the transmissibility, and that is ftr by f0. F0 we know, so we can find the force transmission. So here we would stop this session. So I thank you for attending this lecture, and see you in the next lecture.